Welcome to probability. You are watching probability, but this time is different. You will understand it. That's the beauty of this time. You will understand it, and then you will teach the other kid, and he will understand you. Now, let's try to understand it. But first, you are asking, is it good if I'm in PhD listening to you, master's degree, or maybe in a medical school or wherever? It's good for everybody. Even if you're a programmer, it's good for you. Even if you are doing work at home, it's good for you. It will help you to make rational decisions that no one can match. Okay, let's start it. So probability is probably, as you can see here, no pun intended. Okay, probability is no pun intended. The most misunderstood topic in the field of statistics. Okay, so people often struggle to make rational decisions when dealing with probabilities because it is difficult to judge the likelihood of a complex event. What do I mean by this? I mean that if you don't know if something will occur or not, or the probability that it will occur or it will not occur, now your decision is highly emotional. It's not highly rational. Okay, it's emotional. So you don't know if it will rain, you go to the farm and you started digging. You see, that is emotional decision. It's not rational. But if you know there are seasons of the years, so the probability that it will rain per year, maybe it's wherever times you will go and started farming or digging your farm and planting your seeds in the best time ever. Okay, so making rational decisions, it's accompanied with you knowing probability. So most people knowing it organically, maybe it's wired in their heads that in the next few weeks something will occur. So the information itself, it's already good for you to make a rational decision. But also probability is good for you to make rational decision when it comes to those scenarios that are associated with numbers. Okay. So why do you need probability? Why you need probability? Organization today, business world, face a great deal of uncertainty when they are making decisions. Okay. Probability provides a valuable tool to quantify this uncertainty so that manager can make better decision. And some example of how probability can be used in business are as follows. Let's see what are the real world examples that managers and other business and organizations are using in order to or when they want to make a good decisions, the rational decisions. And these examples these examples, they will show you how probability can be used. Okay, so example of decision making that requires probability. An e-commerce business would like to know the probability that the customer will make a purchase after browsing through a film website for more than 10 minutes. As you can see, if someone browses through your website page for more than 10 minutes, what is the probability that he will make a purchase? Okay, he or she will make a purchase. What is the probability? If you don't know the probability, now you will go and search for the data. Okay, for the data. You have already advertised your web page. Now someone comes and browses for 10 minutes, he doesn't make a purchase. Okay, so within maybe 20 minutes you get probability of getting a purchase is 1. Okay, now what will you do? Okay, it's time now you make a rational decision. Okay, a credit card executive would like to examine the probability that a customer with a poor credit score will be late with his or her next payment. Okay, These are example of decision making that requires probability. A media consultant is asked to determine the probability that the viewing audience for the next year Super Bowl will exceed 130 million people. Okay? A company sales department would like to establish a probability that a male customer will purchase an extended warranty after buying a laptop computer. Okay? So these are the decisions making, the scenarios that needs decision making. Okay? This is a scenario, real world scenario that needs decision making. So if you study probability today, will you get a job like right now? I assure you, if you find a job and you are good at probability, and just give them maybe these examples here, as you can see, these examples, you are good at this, maybe they will think about giving you a position. Okay, let's go. An introduction to probability. So now we were talking about the stories about probability, I mean decision making, what is probability in more organic way, like no pun intended, you see. No, probably we are talking about it. Now let's talk about numbers in probability. What really is probability? So an introduction to probability. A probability is a numerical value. Let's see. It's a numerical value, okay? A numerical value that indicates the chance of likelihood of a specific event occurring, okay? A numerical value. What are those numerical values? Is it like 1 million, 2 million, 250? No. What are those numerical values? A probability is a numerical value ranging. Now we understand what are those numerical values. From 0 to 1, or from 0% to 100%. It indicates the chance or likelihood of a specific event occurring. Okay? A chance or likelihood of a specific event occurring. Let me ask you today, what is the chance or likelihood of a president to visit your house? Is 0, 0, 0, 0. It's 0. Why 0? Because you don't have any business to do with a president, okay? Maybe visiting your house, you see? But there is probabilities that you will visit a White House or a place where the president making campaigns wherever, but not that the president will visit your house. Now we have a 0 probability and we have 1 probability. What is the probability? Today we'll have day and night. Within 24 hours we'll have a day and night. It's 1. We must have a day and we must have a night. It indicates the chance or likelihood of a specific event to occur. If there is no chance of event occurring, the probability is 0. As I told you, the president will not visit your house today, or tomorrow, or the day after tomorrow, because it doesn't have any business to do with your house. If the event is absolutely going to occur, okay, the probability of occurring it is 1. Sindio? Yes. The probability of occurring for events is 1 if it's absolutely going to occur. The day and night it must occur. The Monday, Tuesday, Wednesday, Thursday, it must occur. If one day will be skipped, now we don't have a word. See? If we have month January, February, March, April, if we will not have an April in our counting month, now that is not a full year. The April must be there, okay? The numbers is translated into a percentage. So 1 up to 0 can be translated into a percentage. For example, if an event cannot occur, there is assigned a probability of 0, which is stated as 0%. By contrast, if the event will absolute occur, the probability of occurring is 100%. Today we will have a dark day. We will have a day and a night. A dark day, you know, when you say dark day, someone will think about ghosts and wherever. No one will be. Today you will not have a ghost in your house. Today there will be a night, a peaceful night, and you will sleep quietly. Now let's keep going with probability. Don't talk about emotional decision. We were talking about rational decision, mathematical decisions. So the term are widely used when talking about probability. So the following terms that are widely the terms that are widely used when we are talking about probability. The first term is experiment. So if you want to forget about these terms, you are allowed. If you want to grab this, you grab a pen and a paper and started to write about the terms that are used in probability, you are welcome also. Is really up to you. It's really up to you. So the process of measuring or observing an activity for a purpose of collecting data. Okay? An example is rolling a 6-sided die. Okay? Now we are collecting data about 6-sided die. What data will you collect? Okay? Maybe I ask you. If you don't have an answer, wait, I will give you the answer in the later slides. So the process of measuring it. So catch this: experiment. These are the words that are used in probabilistic questions. There is experiment, there is a sample space. So what is experiment? I've already told you. What is a sample space now? All the possible outcome or result of an experiment. Okay? The sample space are the results of an experiment. The sample space for a single die experiment, this one above here, is the numbers 1, 2, 3, 4, 5, 6. Okay? These are the sample spaces. These are everything that can occur when you toss a die. Okay? Someone will say, when I toss a die, like a roll, maybe example, when I'm rolling a single 6-sided die, when I'm rolling it, something will occur that is number 1 or 2 or 3. It will not occur that I will have all 6 numbers 1, 2, 3, 4, and 6, no, 5, 6. It will occur that you will have all 6 numbers, but in different positions. But the number that is up there, up the die there, is the number that we consider. You consider when you are playing with a die. Okay, when you are playing with rolling a die. Now, if you consider that number only that occurs that on top of the die, or that you are seeing it directly on top of that die, that number is called that number is called. Now we will see what it's called. So statistics put the numbers in braces, okay, to signal that they represent the sample space. So statisticians put the number in braces to signal that they represent the sample space. So respect these braces, they represent a sample space. Don't worry, we didn't even touch probability at all. We just learning the basics that will enable us to touch it very more carefully than when we will touch it without careful learning the basics. So an outcome is just a fancy word for a result. Okay, we have just a word like it's called an outcome. It's a fancy word for a result of an experiment. For example, if I roll a single die and I get a 6, the outcome of experiment is a 6. As we can say that the results of experiment is a 6. So event, one or more outcome of an experiment. Okay, so the outcome or the outcomes is a subset of the sample space. Okay, as you can see, you can get 6 when you toss a die or when you roll a die. Okay, if you get 6, this 6 is just a subset of the entire event. Okay, an example of an event is rolling a pair with 2 dice. Okay, when you roll a pair with 2 dice, this is an example of an event. So simple event, an event with a single outcome in its most basic form. Okay, if you have a single outcome in its basic form, that is, we can call a simple event. That cannot be simplified. You get 5 with 5. You see, you cannot simplify 5 when you see it on top of your die, or you'll see 5 and 5 only. So an example of a simple event is rolling a 5 with a single die. So you get a 5 with a 5. Nothing, no any other way to simplify it. So some other example of experiments and their corresponding sample space. The event rolling a pair with two dice is not a simple event because it contains two outcomes, the number from each die. So you roll the first die and you roll the second die. The first die shows you 1, the second die shows you 4. The total there is 5, but every die shows its different unique number. Now, the event of rolling a pair with two dice is not a simple event because you can add those numbers, you can subtract those numbers that you get. But if it's a simple event, you toss a single die. You see, you are rolling a single die. That is a simple event. But two die is not a simple event because you have two die with showing two different or two same numbers. Those numbers you can go on doing something else with those numbers. You can add them, you can subtract them, you can make like a code for them wherever. So example of experiment and their sample spaces. Example of experiment and their sample spaces. Experiment sample spaces. So flipping a coin, we will have a sample space of a head and a tail. So you know these spaces, they mean sample spaces. Answer a multiple choice question, we will have A, B, C, and D. These are the sample space maybe you will have. For most of exam is A, B, and C. D and E and F and G, those are medical school maybe multiple choice questions. Inspect a product, you will have defective or not defective. Okay. Draw a card from a standard deck. You will have 52 cards in a deck. It's simple to know, to wrap those around your head. There are 3 methods of assigning probability that we'll discuss in this chapter. So, how will you assign probability? Okay. How will you assign probability? So there is a classical probability, there is empirical probability, and subjective probability. Most classes don't teach about classical, empirical, and subjective probability, and it's very new to many. Now I will teach you there are these classical, empirical, and subjective probability. So classical probability. Classical probability is used when we know the number of possible outcomes of the event of interest and can calculate the probability of that event using the equation. Okay? As we know, in a coin we have a head and a tail. This is a classical probability now. The number of possible outcomes. As I've said, that outcome is just a fancy word for a result. The result of tossing a coin is just you will have a head or a tail. The result of getting a baby, maybe it's a boy or a girl. Okay. So as when you toss a die or you roll a die, maybe you will have 1, 2, 3, 4, 5, or 6. If you have a card you must have 52 cards with a lot of symbols inside. Okay. But those symbols are specific. You see. Most people don't know a lot about cards because they don't play cards. Me too included. I didn't play cards a lot. I play a lot of die. I roll a lot of die. I do a lot of gamings that most doesn't involve cards. So when someone says a deck of 52 cards, I want to learn about the 52 cards and play a card, and then I will get to understand cards very well. But today we'll talk about coin and a die. A die, you will see it. A coin, I think you have it in your hand right now. It's not bad about it. So classical probability, the formula for classical probability, it says that if we want to find the probability of A, it's called, we will have a number of possible outcomes that constitute event A, this one, all number, maybe that the number of that possible income, maybe when you toss a die, the number of possible outcomes for a die to show 5 is 1. Okay, maybe if you didn't understand it, if you didn't understand me, you will understand me. Total number of possible outcome in the sample over total number of possible outcome in the sample space. So don't worry about understand it right now. We will do a lot of examples now. You will understand. Okay, so where P of A, the probability of event A that will occur. Okay, so this is the formula for classical probability. If no one told you this, I repeat, this is the formula of a classical probability. So this is a die, for those who didn't know about the die. If you roll a die, you will see maybe 3, maybe 2, maybe 1, maybe 4, or 5, or 6. So if you know all the number of possible outcomes like this, now you are dealing with classical probability. Okay, these are the number of all possible outcomes when you are rolling a die. But you may end up getting 5, you may end up getting 6 or 3 or 2 or 1 or 4. It's widely understood by many. So single die experiment. For our single die experiment, our sample space has a 6 possible outcomes. So we have a 6 possible outcomes. First, 1, 2, 3, 4, 5, 6. These are my possible outcomes, as shown here. So if the simple event A is defined as a rolling a5, which has only one way of occurring, okay, then the probability of event A to occur is calculated as follows. So 1 has only one possible way of occurring. 2 has only one possible way of occurring. It will never appear that you roll a die and you get in a very upper side of a die that a 2 and a 3 and a 4. No, you will get only 2 and only 2. Now, if you will get 2 once, you say the probability of 2 to occur is a 1 over 6, all possible 6 outcomes. Okay, if it's hard to understand there, I will make you understand. Don't worry about it. So if the simple event A is defined as a rolling a 5, you just roll a die and you get a 5, which has only one possible way of occurring. It has really only one possible way of occurring. If you roll a die once, I didn't say you will roll like first, second, third. If you roll like 3 times, you might probably get 5 3 times. It's not my problem. It's the problem of randomness. But if you roll a die once, you will know if any number will occur, it will occur once. Okay, that's the beauty of probability. So now we'll say 1 over 6. 6 are all possible outcomes, but 1 is that probable outcome that 5 will occur, is only once. As you can see the formula here, number of possible outcomes that constitute event A, total number. Now we have a total number of possible outcomes that is in the sample space. Total number of possible outcomes that are in the sample space. So, in other words, there is a 16% probability of rolling a 5. Why do we have a 16% probability of rolling a 5? Because we have 0.16 here, 7, as an answer of 1 over 6. Converting this to percentage, now we have a 16%. In other words, there is 16% probability of rolling a 5. This is an example of a simple probability because we are considering the likelihood of a single simple event occurring by itself. So later in this chapter, we will expand this concept to consider 2 or more events occurring. At the end of these slides, forgive me for talking about chapters here. So classical probability assumes that each event in the sample space has the same likelihood of occurring. That's why we say 1/6. Even if you are being asked about the probability of a die, when you roll a die, number 3 will occur. It's 1/6. 4 will occur 1/6. 5 will occur 1/6. 6 will occur 1/6. Okay. That why? Because classical probability assumes that each event in the sample space has the same likelihood of occurring. If we have 2 5s in a die, now we get 2/6, but no, we have only one-sided 5-point die. That is, the chance of rolling a 1 is the same as rolling a 2, and so forth and so on. You also need to know the total number of possible outcomes in a sample space. Total number, as I've told you, is 6. Okay, that is the total number of possible outcomes. So classical probability. So classical probability requires that you know the number of outcomes or results. This is a fancy word for result. I repeat it. You know the possible number of outcomes that pertain a particular event. You toss a coin, you know the possible number of outcomes is head or tail. You roll a die, you know the possible number of outcomes is 1 up to 6. You also need to know the total number of possible outcomes in the sample space. Okay, so the total number of possible outcomes. So if it's a sample space, I told you, you use curly brackets and you write all the possible outcomes in a coin. We will say head, comma, tail. But for a die, we will say 1, 2, 3, 4, 5, 6. That's it. There is no 7 in a die. Simple probability represents the likelihood of a single simple event occurring by itself. Okay? Simple probability, we just represent the likelihood of a single simple event occurring by itself. So if a sample space includes every possible simple event that can occur, then we say that set of events is collectively exhaustive. You see? So if the sample space include every possible simple event that can occur. So in your experiment, you have been told that to collect every single simple event that can occur. It's called exhaustive, collectively exhaustive event. This event is called collectively exhaustive event. Example, you have been told that to collect the rankings of your teachers. Maybe the rankings, we have good, we have worse, we have bad, we have excellent. So you have a lot of the way to rank a person: kind, sharp, smart, wherever. It's collectively exhaustive event if you collect every possible, let's say, if the sample space include every possible simple event that can occur, then we say that set of events is collectively exhaustive. Sounds like how I feel when I'm trying to make my publishers writing deadlines. It sounds like that. You see, if you are publishing something and you want to meet a deadline, that event is exhaustive. A lot of it's exhaustive, but don't compare it to that. It's just a joke. Okay. So for example, the events 1, 2, 3, 4, 5, 6 are collectively exhaustive when we roll a single die. When we roll the die, one of these outcomes must occur. We can expand our classical probability example to roll 2 die. Okay? This changes the sample space. So we don't roll the die twice, but we roll 2 die. The first hand will have die, and the second hand will have another die, and we roll them together. So this changes the sample space to the following one, which has 36 possible outcomes Each pair of a number represents the outcome of 2 dice. Okay, let's define event A as obtaining a sum of 5. So before we proceed, let's shift now into our blackboard for more understanding. Let's shift into our blackboard here. Before things started to get more complicated, let's look at our blackboard here. So Richard Feynman, one of our best known smart scientists, said that teaching as the best tool you can use to understand teaching. You can teach in order to understand something. This is one of the strongest tool in trying to understanding stuff. So for me, just I would like to know the probability that I will become the best teacher. You see, in probability, the question is how. You see, what are the methods to come up with the best answer? Okay, so I want to calculate the probability. Right now, I would like to know the probability that I will become the best teacher. So what data will I collect? You see, the question is how also will I collect, and what are the methods to come up with the best answer. So in my experiment, I choose to have good, excellent, fail, not at all. Created a questionnaire and submit it to other teachers, maybe professional teachers in universities, and ask them, is my teaching good, excellent, fail, or not at all? We don't need you to teach at all. So the results as outcome were as follows. Set things up. I started to set things up, you see, like a survey. I give to those teachers those surveys about ranking my teaching. So teach in front of the other teachers and give them papers to survey also. And for when I count, there are those who said my teaching is good, were 10, excellent were 5, fail is 1, and not fail is 1. So 17 teachers participated. It was like a lot of small sample size I have here for those who participated in my teaching rankings. So good, in percentages, you take 10 divided by 17, you get 0.588. Okay, 58% of teachers said I have a probability of becoming the best teachers in the best teacher in the long run, and 29% of teachers said I have a probability of 29% being an excellent teacher in the long run, and let's say 0.05, now this is 0.5, like 0%, said that I have failed to be the teacher. Okay, this is all about understanding probability. So these were my sample space, and these were my outcomes for each probability that I will become one of these. So I think my story there started to make sense with you, started to understand probability. Like, this is the story. This is just a story I gave you about probability. Another story. Let's look about. Have you ever been asked, like, in the scale of 1 to 10? Let me give you this story in order to understand probability. So, have you ever been asked, like, in the scale of 1 to 10, how can you rate your beauty, maybe? You see? How can you rate your beauty? Someone says 7, someone says 6, someone says 8. You see? So I have a problem here. Why did you choose like 7, 6, and 8? Is no anyone who can choose like 2? So no one likes to be like looked ugly. You see, everyone wants to be looked like in the scale of 1 to 10, started from 7 to from 6, 7, and 8. Okay, at least 6 is kind to rank someone in 6, but we really don't know who is 10. You see, who will rank himself 10? Will he believe he's 10? And will a person believe he's 10? Or just by letting him know that his beauty is 10 is enough for him to understand or to believe he's 10? So there are two schools of thought. If he started to believe in himself about and ranking himself like 10, that is a school of thought of believing hard in yourself. And there is another school of thought. If we tell him in the scale of 1 to 10, you are 10, according to our experiment, now he will get into our numbers and our experiment and ask why. How did you collect? I'm interested with what peoples were participated. You see, like if people who were suspected were full ugly, maybe I'm the most beautiful of them all. You see, it's a ranking. It's just a ranking. So that is why probability is still something that need more convincing power. So that is why probability is something that you can put in your mind as that needs more convincing power. Like, the question is, how can you set up your probability scenario? Okay, how can you set up your probability scenario? You say you give someone a comment that you are building in a scale of 1 to 10, you are 10. Press on the first question is that in order to convince me, you just mumbo jumbo around like throwing words. I want you to tell me, you see, like in a scale of 1 to 10, what were your question in your experiment? Who has participated? You see? And make it sound mathematically true. So your scenario must be sound mathematically true for a person, and qualitatively true, I mean. So in a facts world, it must have concepts also. Facts of history, facts of from like Neanderthal until today. Why Neanderthal is not cute as you see, things like that. So beautiful. So because we believe both by numbers and by facts, now we know that if someone come up with this scenario of giving me 10 in a scale of 1 to 10 of beauty, he's the lie. Okay, because we believe in numbers and facts. So if you will give me only the number, still I will not believe you. Give me the facts. The fact is ABC, so I don't believe you. So your fact does not count in the best way. You see, there are best ways to count. So short representation of probability, as I've told you, number of events over total number of events or sample space. This is the formula. I told you we will get out a little bit and get a blackboard. This is our blackboard. So example, in every 3 video I will show my face once. You see, what is the probability of showing my face in 10 videos? Okay, so in every 3 video I will show my face. So first 3, second 3, third 3, and 10th 3. So what is the probability of showing my face in 10 videos? So the probability is 1, 2, 3 is 3 over 10. So number of events over number of samples, total number of events or number of sample space is 3 over 10. Okay, so in this scenario now of rolling a dice, you will excuse me if I'm going with wrong frequency. As you see, I'm still ranking in teaching. You can rank me also down the video there. So rolling 2 dice, 1, 2, 3, so every dice has a sample space of 1 up to 6. So the first dice has a sample space of 1 up to 6, and the second dice has a sample space of 1 to 6. You are being told to find the probability of getting a sum of 8. A sum of 8, as you know, is 4 plus 4 is equal to 8. 6 plus 2 is equal to 8. 7 plus 1 is equal to 8. What else? Maybe 5 plus 3 is equal to 8, wherever, okay? And those numbers must be below 6, those numbers which can add to 8, okay? Those two numbers which can add to 8. Now let's get interested. Now we don't get political, we say we get interested. So a lot of politics were going around, but now we are getting to let's getting now daily in mathematics. So click it down there, click again, there it is. So when you roll 2 dice, the first dice sample space will be 1, 2, 3, 4, 5, 6, okay? And the second dice sample space will be the same, 1, 2, 3, 4, 5, 6. So if you roll 2 dice, you know occurrence maybe will be 1, 1, or maybe will be 2, 1, or maybe will be 3, 1, 4, 1, 5, 1, 6, 1. Okay? Also occurrence, you see, you take this number, this is the first number and this is the second number. So you say 1, 2, so then you say 1, 2, then 2, 2, then this one and this one, 3, 2, 4, 2. All of these are possible outcome. 5, 2, 6, 2. You see, all of these are possible outcome. Also, you might have get, let's say 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3. So now we get what? 4. So 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 4. Now we get what? 5. 1, 5, 2, 5, 3, 5, 4, 5, 6, 5, 5, 6, 5. Okay, now we get 6, 6. So 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. So all of these are the possible outcomes of what will occur in a dice, okay? Or when you roll 2 dice with a sample space of 6 each. So you can get 6 in all possible outcome of 1, of 2, of 3, of 4, of 5, of 6. You can get also 5 of all possible outcome, 4 of all possible outcomes, 3 of all possible outcome, 2 of all. So what am I talking about is like the first dice may have 4, but the same as the second dice when it has 1. We have also 4. That's all of these are the possible outcomes. I think you get me. The second dice also, another toss will have 4 and 3. It's not another toss, like the same toss may have all of this possible outcome. That is what I mean. It's not like we toss every time. So before you toss, all these are the possible outcomes that you can get. You can get 3 this side and 3 this side, 4 this side, 4 this side, 5 this side, 5 this side, 5 this side, 4 this side, wherever, you see. Now, so find the probability of getting the sum of 8. So we didn't get the job done here. We will have to do the final thing here. So 8, the total of 8. Here we have the total of 8. Yes, okay, this one here. Let me choose the different color here. Sorry. Yeah. So this sums to 8. This, you see, diagonally, you see, diagonally. So this 1 2 3 4 5, you see, sums to 8. Also, what sums to 8 also. So don't skip a number. Don't skip a number. So what is the best way to find those numbers that sums to 8? For me, I get the diagonal relationship. What is another best way? Any other number that sums to 8? Let's pass 7 6 5 4 3. This year we get 4 5 6 7 5 6 7 9 10 6 8 6 7 9 10 11. So the numbers that sums to 8 are in this diagonal here. Now, how many are those? So there are 1 2 3 4 5. Oh, let's start 1 2 3 4 5. So there are 5 over what? 36. So there are 5 over what? Where did I get 36? Count these boxes. 1 2 3 4 of all possible, 5 6 of all possible outcomes. And this 1 2 3 4 5 6. So for all possible income we get 6 times 6. That way we get number of all total of all possible outcomes is 36. So the probability of getting a total of 8 or a sum of 8 is equal to 5 over 36. So here we get probability of the sum of 8 is equal to 5 over 36. So if someone just said we have another place to get the sum of 8, just comment in the video description below. But I'm not that bad slow in math. I'm just joking. So keep watching. We'll go to another. We'll return to our slide there, and this is just to show you that I can get out of a slide and do math. So don't worry about the future video solving a lot of math. Okay, let's get back to our slide. After looking at that example we look at the example of 2 rolled dices, and we get a table and we get a number of possible outcomes before we toss those dice, and we do some math there, interesting math, and people were like shouting out about it. So for example, the event of 1, 2, 3, 4, 5, 6 are collectively exhaustive. We were talking about exhaustive, collectively exhaustive events. Are collectively exhaustive when we roll a single die. So when we roll the die, one of these outcomes must occur. We can expand our classical probability example into rolling 2 dice, and that example were the example of when you roll 2 dice. So this changes the sample space to the following one, which has 36 possible outcomes, and you know we see there are 36 possible outcomes. Each pair of numbers represent the outcome of 2 dice. So each pair of number, as we see there, represents each pair of number represent the outcome of 2 dice. So we were having pairs of numbers like there, like we get 1 2 3. So 1 2 3 4 up to 6, and here up to 6, and we get 2, 1 2, 2 2, 3 2, 4 2, 5 2, 6. We get this. Okay, so This changes the sample space to be 36. We count all of the possible outcomes here, and we say there are 36 even before we toss the two dice. And we roll the two dice. It depends on the English in which you like it. Okay, so each pair of the number represents the outcome of two dice. Let's define event A as obtaining a sum of 5. Okay, there are 4 ways in which a sum of 5 could be rolled. They are highlighted in yellow in the following sample space. So let's see. It's always in a diagonal. Okay, it's always in a diagonal. So the sum of 5 stated by in 1, 4 and roll down up to here. It's always in a diagonal. A sum of any number. The sum of any number is always in there. The sum of 6. Let's say the sum of 6. When you see 1 plus 5 is equal to 6, you see the diagonal. The diagonal. The sum of 6 is in diagonal. The sum of 7 is in diagonal. The sum of 8 is in diagonal. The sum of 9 is in diagonal. The sum of 8 is in diagonal. The sum of 9, the sum of 10, the sum of 11, the sum of 12 is in diagonal. So don't worry about the sum of, it's simply in diagonals of 2 rolled dices. Even how can you roll 3 dice? What will be the possible outcome? A lot. We can now calculate the probability of rolling a sum of 5 with our 2 dice. So it becomes, because there are 4 ways to obtain a sum of 5 out of 36 possible outcomes, the probability itself will be 4 over 36 and will be 0.1111, okay, which is 11%. In other words, there are 11% chance of 2 dice summing to the number 5. Okay, let's conclude here. So what is the probability of obtaining a sum of 8 when rolling 2 dice? So we have already solved that, the sum of 8. Maybe now I want you the probability of getting 11. Okay, sum of 11. Okay, if you get it, maybe let's jump it here. Right, what is our diagonal which sums to 11? Is this one? Which one? This is 9, this is 10, this is 11. Now that its diagonal is this one, so it's 2 over 36, which is equal to probability itself, probability of getting what? The sum of 11. Okay, you can leave it in fraction. Don't afraid to go into decimal. Don't afraid to go deeper than decimal even. You are allowed. Okay, I think we are done here in the about classical probability. We'll move on to empirical probability. And what is the final one? And subjective probability. And subjective probability. So we do classical, we are done with classical. Now we are moving into empirical probability, finally subjective probability. So when we are completed one of these, you will get another tick here about getting it. Okay, thank you.